A game that mathematics guarantees is a bargain no matter what you pay, and yet nobody buys it. Here is a game whose rules fit in a single line. You flip a single coin until it comes up heads, that's all. Yet when you price this game with the standard yardstick of mathematics, you get an answer you cannot deny. Infinity. Charge 100 million won to enter, charge 1 trillion won, the calculator still says, a bargain. So, how much would you pay to play this game? Everything you own? Probably not. Look at the rules and anyone hesitates. Half the time this game hands you a mere 2-1 and ends. On one side, a calculation that says infinity. On the other, a gut feeling that says, a few thousand won at most. Today's story is the St. Petersburg paradox, born in 1713 from a single letter within the Bernoulli family. First, let me nail down the rules. 1 coin and the prize doubles each time. You keep flipping a fair 50-50 coin until it comes up heads. If heads comes up on the very first flip, the prize is 2-1. Each time heads is delayed by one more flip, the prize doubles. On the second for 1, the third 8-1, the fourth 16-1. The moment heads appears, the game ends, and you collect the prize that has piled up until then. The longer tails holds out, the bigger the jackpot. 9 tails in a row, then heads, and the prize is 1,024 won. Let tails hold out 29 times and it's about 1 billion won. If the coin keeps landing tails, you're a billionaire on the spot. The catch is the entry fee. What should the casino charge to make it fair? Before we calculate, settle on your own answer. You'll meet that number again at the end of the video. The tool built to answer exactly this kind of question is the expected value. Its meaning is humble. If you play this game a great many times, how much do you take home per round on average? For practice, try it on an easy game. Flip a coin once. Heads pays 1,001, tails pays nothing. You collect 1,001 about once every 2 rounds, so on average 501 per round. The fair entry fee is 501. Now apply the same yardstick to our game. Multiply each prize by its probability, then add them all up. The chance of ending at 2-1 is 1/2. Its contribution to the average is half of 2-1, 1-1. The chance of ending at 4-1 is 1/4. Its contribution is 1/4 of 4-1, again 1-1. The chance of ending at 8-1 shrinks to 1/8, but the prize has grown to 8-1, so the contribution is again 1-1. See the pattern? The prize doubles while the probability halves, so every line contributes exactly the same 1-1. And this list never ends. 1 + 1 + 1 forever. And if you trust this yardstick, there's only one conclusion. Whatever the entry fee, always play. The figure below dissects the structure that produces this infinity. And yet, nobody opens their wallet. Look at the left panel of the figure. Half of all rounds end on the very first flip at 2-1. The chance of ending at 4-1 or less is 75%, at 8-1 or less, 87.5%. The jackpot exists, but it sits brutally far away. For the prize to top 1 million won, tails must come up 19 times in a row, a chance of about 1 in 520,000. The right panel is the heart of the paradox. Each of those trifling lines is all the same, a brick worth exactly 1-1. A probability near 0 times a prize near infinity. This product survives as 1-1 per line, added on without end. The philosopher of science and hacking put it flatly in 1980, few people would pay even $25 to play this game. With Monty Hall, intuition was wrong. Here it's the reverse. The calculation is right and no one accepts it. Now let's put a computer through 1 million rounds and watch the average crawl toward infinity. Since the expected value was defined as the average over many repetitions, we simply repeat it many times for real. Here the same million-round experiment is run 3 times with different luck and drawn overlaid. Look at the actual tallies. Half end at 2-1, 87.5% at 8-1 or less, and yet the average is a mere 24.71. The figure tells 2 stories. First, the average truly never settles on any value. In an ordinary game, the more rounds you play, the more calmly the average sticks near the expected value. That's the law of large numbers. But this game's average stays forever unruly. It leaps up a step on a jackpot, gets pressed down by common rounds, and the three curves don't even resemble each other. Second, the average does grow after all, just cruelly slowly. 1,000,000 rounds thrown and the average prize is 24.71. The other two experiments about 38.1 and 18.1. All pocket change. The giant of probability theory, William Feller, measured the exact speed of this sluggish growth, roughly log base 2 of n. The guideline hits about 21 at 1,000,000 rounds, so to see double that 41 you need 1,000,000 rounds squared, that is, 1,000,000,000,000 rounds. So the expected value is infinite is no lie. The average does grow without bound. It's just not an infinity you'll live to touch. So where did this name come from? Let's step back 300 years for a moment. The birthplace of this problem is, in fact, not Russia. In September 1713, the Basel mathematician Nicolas Bernoulli first raised it in a letter to the Parisian probabilist Montmort. If the name Bernoulli sounds familiar, you're right, Jacob and Johann of calculus fame, and Daniel of fluid dynamics. An aside, the original used not a coin but a die, a game of rolling until a 6 came up. The problem drifted through mathematicians' letters for nearly 25 years, tormenting everyone. Then in 1738, Nicolas's cousin Daniel Bernoulli finally published a paper with a solution. The place the young Daniel worked was the St. Petersburg Academy of Sciences in Russia. That's exactly where the paper appeared, too. So the paradox took its name not from Basel where it was born, nor Paris where it was delivered, but from the city where the solution was published. Bernoulli's prescription. The same money can carry a different weight. Daniel's starting point is a humble question. Is the amount of money the same as its value? To a thirsty person, 1 glass of water is worth a fortune. The second is welcome, the fifth is meh, the 10th is torture. Money is the same. To someone whose entire wealth is 1,001, 1,000,001 changes their life. To someone worth hundreds of trillions of one, it's loose change that barely moves the needle. The more you already have, the smaller the joy of each additional bill. Economics calls this intuition, diminishing marginal utility. So Daniel changes the yardstick. Multiply probability not by the amount, but by the satisfaction the prize brings, its utility. The shape of utility he chose is this. Happiness grows not with the amount of money, but with the number of its digits. It means that every time your wealth doubles, your joy rises by the same 1 step. In the language of mathematics, that's a logarithm. Let's remeasure the game with this new ruler. A prize of 2-1 is 1 step of happiness. For 1, 2 steps. 8-1, 3 steps. The moment the runaway prize is tamed, infinity vanishes too. Computing the expected happiness. 1/2 times 1 step, 1/4 times 2 steps, 1/8 times 3 steps. And the cash matching 2 steps of happiness is 2 taken to the power of 2 for 1. The left figure is Bernoulli's ruler. The prize surging up without ceasing, and beside it, happiness climbing just 1 step at a time. The once infinite price tag became a mere 4-1. Absurdly stingy, but this side is the one that agrees with our gut. An aside, the first at bat was actually someone else. In 1728, Kramer of Geneva put nearly the same idea in a letter. Medicine is only medicine, not a cure-all. In 1934, Menger built a game where happiness doubles each time, dragging infinity back out even with the log ruler. There's one more prescription that deflates the infinity without even reaching for utility. A thoroughly worldly one. But that money, who pays it? If tails comes up 39 times in a row, the casino must pay out about 1.1 trillion won. At 49 times it tops 1,000 trillion won. And the moment a payout cap appears, the expected value calculation gives a completely different answer. Run the numbers and the result is shockingly trivial. Every time the casino's vault doubles, the fair entry fee rises by exactly 1 won. A neighborhood arcade guaranteeing up to about 1,000,000 won, 21 won. A big corporate casino guaranteeing up to about 1 trillion won, a mere 41 won. In the end, infinite expected value was a number that holds only when a bank with an infinite balance guarantees infinitely many rounds. The right figure is that honest bank. The horizontal axis runs from 1,000,000 won to 1 quintillion won, a log scale where one tick is 1,000,000 times the last. And still the fair entry fee only crawls from 21,1 to 61,1. The infinity monster becomes pocket change the moment it sets foot in a finite world. Now we can lay out the paradox from start to finish in a single breath. The calculation that the expected value is infinite is correct. No trickery, no mistake. But for that number to mean anything, two infinities are required. Our lives and the casino's balance are both finite. In that finite world, what you meet is not the average but a single outcome. And that outcome is half the time 2-1. Your gut knew this from the very start. It's not that the yardstick of expected value is wrong. It's that this game stood outside the world where the yardstick works. And this puzzle didn't end with one pocket change game. The concept of utility Daniel Forged already explained within the same paper, when it's rational for a merchant to buy insurance. Humans who avoid risk, money that grows lighter the more you hold. Some 200 years later, this intuition was refined into von Neumann and Morgenstern's expected utility theory. And it became a cornerstone of modern economics and finance. A single coin toss puzzle turned out to be the midwife of an entire discipline. Here's the summary in 3 lines. Next time someone tries to sell you on the expected value is this huge, so it's a sure win, quietly ask just 2 things back. If you carry these 2 questions, you're already standing on the same side as Bernoulli 300 years ago. So, let's return to that number you fixed in your mind back in part 1. What was your entry fee? If it was pocket change and not infinity, congratulations. Your gut already knew 300 years worth of math. It's somewhere between 4-1 and 61-1. If you enjoyed today's journey, support it with a subscribe and a like. See you at ELLS Lab for the next Odyssey.